Okay, so one example from your book, it talks about World Series baseball, and I know we have some baseball players in the room, so I wanted to, well, not in, dang it, not in the room, right? We're all in different rooms, but I know we have some baseball players in this class, so I wanted to keep this one in there. My brother's a huge fan of the Chicago Cubs because we grew up in Ohio, so that's a pretty close MLB team, so he was very excited. I think that was 2018 maybe when the Cubs won the World Series. I forget what year it was, but it was a very exciting year for him. He was actually at the World Series championship game, which was insane. Anyway, for those of you who are unfamiliar, the Baseball World Series consists of up to 7 games. The first team to win 4 games wins the series. That's pretty standard with a lot of tournaments in professional sports. The first 2 are played at one team's home ballpark. The next 3 are at the other team's ballpark. And the final 2, if needed, are played back at the first park. Recordings over the past century show that there is a home field advantage. The home team has about a 55% chance of winning any game. Does the current system of alternating ballparks even out the home field advantage? How often will the team that begins at home win the series? So I'm not going to have us go through and run the simulation because we just ran a simulation, and I want to respect your time because I do know that you guys are taking stats as an elective course. So I just wanted to answer these questions in a more straightforward way than we did in the previous simulation. If you would like to practice running a simulation, you're welcome to practice running a simulation here, but I do want to respect your time because I know you have classes that are more important right now. So setting up a simulation, what is the component to be repeated? The component that we're repeating is one game. We're just going to see who wins, and we're going to repeat a bunch of different games. So how will we model each component from equally likely random digits? Well, we know what percentages, so we're going to label our numbers from 0 to 99 in total. We know that the home team has a 55% chance of winning any game. So we're going to give the home team numbers 0 to 54 and the visiting team 55 to 99. How will we model? We're going to generate components until one team wins. So we're going to look at 2 digits on our random number table again and again until one team wins the series. So remember, a win is they have to win 4 games out of 7 total. So once a team wins 4 games, it's not like they play the rest of them. So let's say the Cubs versus the Bears. Let's just keep it all in Chicago. Then we would have like if the Cubs win 4 games in a row, then the series is just over. We wouldn't have to go back and forth. Okay, so the response is who wins the series. That's our response variable. And how will you analyze the response variable? You're going to calculate the proportion of wins by the team that starts at home. So you're going to see what the proportion of wins are from the team that starts at home. That is how you're going to conduct this survey. So the final thing I want to talk about is statistical significance. So when you're running a simulation, you want to know if the likelihood of the outcome that you got is similar to, is statistically significant. So if our outcome appears so unusual that it isn't likely to happen by chance, we would consider this outcome to be statistically significant. So here's an example from your textbook. Foresters know that historically about 10% of trees in a certain national forest have been infested with bark beetles. This spring, though, they found signs of the beetles in 8 out of 50 randomly chosen trees. Is this apparent increase in beetle infestation statistically significant? In other words, is finding 8 of 50 trees infested so unlikely that the foresters should be concerned that the true rate is now higher than 10%? So if you wanted to use a simulation, this explains out how to conduct a simulation. I'm sure you can imagine we're just going to label things 0 to 9. 0's the beetle, 1 to 9 is the tree that is not infested because there's a 10% chance that the trees are infested. We're going to look at 50 trees a bunch of different times, which we're just running a simulation, so we're not actually looking at 50 trees. We're just looking at 50 digits and seeing how many bugs are there. So here's the table summarizing the results. As you can see, the number that's infested is the 2, 6, 5, 4, all that kind of stuff. So in my simulation, I found 8 or more infested trees once in 10 trials, right? The only time that we had more than 8 infested trees was this one when there were 9 infested trees out of 50. So maybe the beetle problem is really no worse than the outcome that the foresters observed happened just by chance. However, only once in 10 trials seems somewhat unusual, so the foresters should probably check more trees. If they only checked 50 trees, that's not a good representation of the whole population. Remember in the sampling unit how we talked about you typically want your sample to be at least 100 people. So I recommend that they check more trees because when they have more data points, then their statistics are more relevant and accurate. When you are conducting experiments, the whole point of that is you're trying to see if your experiment proves anything. So statisticians love experiments. They love running simulations. When we have the results of an experiment, we can make a conclusion about whether or not our treatment actually caused any change, whether or not our conclusion can be drawn. When we run a simulation and randomly assign the observed results into 2 groups, we can see if the change we observed is statistically significant. So we can look at whether or not what we observed is different than what was expected, and so on and so forth. So thank you for sticking with me. Those of you who watch these videos, I truly appreciate that you are doing what is expected of you during this time. For your assignment for this week, I am just going to have you do another My Math Lab assignment, 311 using randomness, homework number 13. My other math classes this week, because it is a full week of lessons, they are getting 2 assignments. I'm going to be more lenient with you guys this week because I know, again, you are all in very rigorous classes as seniors, so this is your 1 assignment for the week, so I am going to ask that you truly put in the time and effort into this assignment. I'm going to respect your time and know that stats is probably not your number 1 class that you're focusing on because it's not a graduation requirement. So please use this extra time that I'm giving you this week to focus on those other classes. I'm not going to promise that every week I'm only going to give you 1 assignment. I just want to be respectful of your time, and I know that as seniors especially, this is such a hard time for you because things seem like they're going completely against how you thought your senior year would go. So I want to give you time to kind of cope with the new reality that we're facing right now. So your My Math Lab is your only assignment for this week. But again, in the weeks to come, it is very likely you'll have more than 1 assignment. I do want to just let you guys know I am available through email. If you have any questions for me, I have not yet, as I'm recording this, had any stat students reach out to me for help. So I do just want to remind you I'm available to help you, and I would love to help you in whatever way I can while we're going through this. Even if it has nothing to do with statistics and you're just really struggling with this time, and if you want someone to talk to, you're welcome to email me. Just remember that our school policy is still to have your parents copied in that email, just so we are all staying safe on the internet. Okay, thank you for sticking with me. I appreciate you guys, and I hope you are doing well.